Okay, so in this video, I'll be answering a discussion forum question regarding the derivation of coefficient of performance for heat pumps and refrigeration and the relationship together, and for reversible heat pump and refrigeration. But before we look at that, we'll start off with heat engines because it will give us a basic understanding how everything works, the equations and everything. So in a heat engine, what's happening is that we have heat being produced, which is doing the work. So work net out is equals to work out minus work in. So the work being produced out is greater than the work in. Like our car engine, it makes a car move. So if we take the same system and we say like it's a closed system and it's running on a steady state, but it's also a cycle. What cycle means is that the initial position where we start and where we end is the exact same position. So the internal energy at the start would be the same as at the end. So delta U becomes 0, and then when we apply first law on our system, summation Q minus summation work is equals to delta U, but in our case it's 0. So we come up with a general equation after applying a first law, which is Q in minus Q out is equal to work net out. Q in minus Q out. This is very important because this later subs in to our performance equation. So performance is basically measured by the desired outcome, like what are we looking for in our system to do. In our case, in a heat engine, for example, take the car engine, we're looking for it to do some work. So the work net is what we really need, but what's the driving force? What do we require to make that happen? We need heat. It's a heat engine. So Q in is our required cost to produce the work. So the performance thermal efficiency for a heat engine would be work net out divided by what's causing the work to happen, which is Q in. And then we know that work net out, this thing, is basically Q in minus Q out. When we sub that in over here, we get Q in minus Q out divided by, we have it over here, Q in. So if we divide it individually, these cancel out, this becomes 1. So 1 minus Q out over Q in. So that's how we derive thermal efficiency for a heat engine. Again, we applied the first law on our system being closed, steady state, and a cycle. Given that our internal energy is equal to 0, we get this equation over here, which is work net out. We take this and we put it in our thermal efficiency, which is basically what we need over what is required for us to get there. We need work to be done by our car to make it move, the car's engine to make the car move, which is work net out. But we need to produce heat, which comes from our fuel, which is Q in. So we sub that in, simplify that out, and this is it. So we can further change this and this notation to QL and QH, because we know that Q out in a heat engine, it takes heat from a high temperature reservoir, which is a QH, which is high temperature reservoir, whatever, and similarly low temperature reservoir. So Q out from a heat engine, the radiator of a car, it's throwing heat out into our surroundings, which is at a lower temperature than our car's engine, which is actually really hot. but it's taking, our engine is taking heat in. The heat in is from the combustion chamber where the temperature are extremely high. So we get 1 minus QL over QH. So if we know that Q out is QL and Q in is QH, we can change our initial equation of work net out into this, which is, as you can see, which is work net out is QH minus QL. Okay, so to talk about refrigeration and heat pumps, so we need to understand that it's a similar system. We do exact same process on taking it as a cycle, steady state, and a closed system. So what we do is that we apply first law on it and we derive the work net in this equation. So what this is that how it's different from an heat engine is that instead of work net out, we get work net in, because in a heat engine there's work going outside of the heat engine. The heat is the driving force in that engine and it's causing the work. But in a refrigeration, we are giving work into the system to get heat transfer being done. So like our refrigeration in our houses take electricity as work in so that it can keep our things inside cold. What it does, the electricity provides work in to cause heat transfer from inside the refrigeration to outside, making the insides of the refrigerator cold. So we have work in, and then there's QH from a high temperature reservoir minus QL to a low temperature reservoir. And the coefficient of performance is for refrigeration is basically what do we need, what are we looking for, what are we really interested in. In a refrigeration, we're really concerned about the Q at the low reservoir, which is inside our refrigeration, the area that we want to keep cool. So the QL is our area of interest, and what is going into our system, what's the cost for maintaining that cold temperature inside our refrigeration. What's the cost? It's work net in, and we know work net in is equal to QH minus QL. We just sub that in over here, simplify it to get this equation. Similarly, heat pumps. So the difference between refrigeration and heat pumps is basically what we're looking for. In refrigeration, we're mainly interested in the QL, which is the area inside the refrigerator that we want to keep cool. That's where the QL is. But in heat pumps, we're pumping heat, and we're main concerned is to have the area being heated, and we need to raise the temperature. Instead of decreasing the temperature, we want to raise the temperature. We want to add heat in our environment. Like if you have a small heater in your room, you have electrical heater in your room, you're putting electrical work, and you have a fan and a bunch of coils, and then fan blows on those coils being powered by electricity, and then heat is dispersed off in your room. So we're mainly concerned about the QH. So that's how these two differ. QH over work net in. We know that work net in is QH minus QL. Again, this equation comes from applying first law and simplifying it. So once we have our work net in is here QH minus QL, we just sub that in again over here, simplify it. This is QH, this is not plus 1, this is QH, because QH is what we're looking for in a heat pump. This is our desired output, and this is our input, the work net in, like what's going into our system to have the desired output, right? So we simplify it, and this is what we get. Now, as these two cycles, the system is quite similar, that there's work going in to a system, and there's heat taken from the low temperature reservoir to the high temperature reservoir. But how they're connected is that where in refrigeration, where main concern is QL, but in heat pump, it's the reverse. We're mainly concerned about QH. Everything else is the same. Work net in, work net in. The only thing that's changing is QL and QH. For heat pump is QH, for refrigeration is QL. And how they're connected is that heat pump would always be subtraction of the coefficient of refrigeration would be equal to 1. So the heat pump and the refrigeration cycles are both connected. Their coefficients of performance are connected in a way that coefficient of performance of heat pump can never be less than 1. Why? If we move this over here, it's 1 plus coefficient of performance for refrigeration. So 1 plus this would give you COP-HP. So that's how heat pumps relation is to the refrigeration. They're really closely connected, both of these. So in all our derivation, we see that the final equation has QL, QH, QH, QL, and even for our heat engine, we have QL and QH. Now you mentioned that says that for a reversible heat pump, refrigeration, or the heat engine, the equations for the efficiency or the performance is given in TL, TH. What that means is that we're talking about a reversible process which basically leaves no traces on its surrounding, that it's an ideal case scenario which does not really exist in real life, real conditions, because there's always some irreversibilities in the form of friction, noise, or some other losses. But if those do not exist at all, we have ideal cycle called Carnot cycle, and based on that, that cycle, the Carnot cycle, gives us the ideal and the perfect efficiency for refrigeration, for a heat pump, refrigeration, or a heat engine to operate in. It gives us the perfect conditions and gives us the boundary, like a boundary line. Like it can never reach 100%, but it gives us a ceiling, the realistic ceiling that is possible. Let's say that is 75% Carnot. That is the physically possible limitation of refrigeration heat pump or an heat engine. But to get that, we say that the QL is equals to TL, and it operates between TH and TL. So QL gets converted in TL and QH gets converted into TH. So when we're talking about a Carnot of a refrigeration cycle, this QH would be a TH and QL would be a TL, and same goes here, TL, TH. But remember that each Carnot cycle is all the processes in that cycle are completely reversible. It's ideal case scenario. That's why in a reversible equation, if you say that you want COP HP reversible, the only thing that you need to change in this final derivation would be that this would be TL and this would be TH. Same goes for refrigeration. You need to change QH but QL for a reversible Carnot conditions.